All right, I just wanted to go over the problem solving sheet, the first one, if you missed class, and then also because of the snow day to keep my two classes together. So some of you missed because of snow, and some of you missed today, so we're going to go over that. All right. Okay, so let's look at this one right here. And again, we talked about this one in class, but one thing I wanted to remind you that the ones position is right there. And then like the names like tens and tenths with a THS go on the opposite of ones. So like if you know that this is 300, on the other side is hundredths, like 900ths. And we talked about rounding the other day and how like if you round something and you're only rounding say to the hundreds, this little detail doesn't matter. So if you're rounding to the hundreds, you only look behind because that's how accurate you want to be. This stuff is too tiny to matter. And for less, you leave this alone, but you do have to fill in so that it's in the hundreds position. So when you round to like the hundreds, you have to have hundreds, no decimals. If you round to the thousands, so if there's say a 1 here and the 3 would say, oh, leave that alone. So then it's 1,000 and you fill in with zeros, but no decimals. If you're rounding to a decimal place, so if I'm rounding to the nearest tenth, then if you have a decimal, it ends where you say it's going to end. So tenths would end in the tenths, hundredths, and so forth. So the 9 would say round that up. But again, I said to round to the tenths, it has to end there. This gets kind of tricky where if I give you something like 499.9943 or something. Okay, so if I say to round to the nearest 1, the problem is this 9 says, ooh, make it a 10. That means make this guy 1 more, make that a 10, carry that up, and it's 500. But you didn't, this looks like you rounded to the 100 because you only have a digit in the hundreds with zeros. So it doesn't really look like you rounded to the ones. So we put a decimal here to say, oh no, that 0 matters. Like that means I rounded there. The same problem if you round to the 10th, we're going to have that same issue. This 9 is going to make that a 10, which makes that a 10, which makes that a 10, which makes that a 5. But we don't quite write it the same because remember with decimals, if you say you're rounding to the 10th, it has to end in that decimal place. So you put a 0 to indicate that you rounded to the 10th. Okay, so decimals end where you round to. Tenths, hundredths, thousandths, 10,000ths. Whole numbers, if you round to the 100, you're going to have a digit in the hundreds position with zeros after if you round to the 1,000, and you wouldn't have any decimals if you're rounding to that. All right, we talked about estimating. My math lab probably is going to want you to use the rounding rules. So they would probably say, oh, round that down to 70, round that up to 30, and just add like that. Estimating means you do it in your head. You don't use a calculator. Some people might be like, well, Julie, I know 75 cents and 25 cents makes $1. So I would maybe do that, like round 1 up, 1 down. I'm okay with that. Just watch my math lab, see what they do. Some people might just, like if you're in the grocery store, you might round them both up so you don't run out of money, So you might be like, I'm not going to round that down to $70. I'm just going to say, okay, maybe I round it to $80 and $30 just to be safe that, especially if you're, oopsie, got an extra 1 in there. Especially if you're paying cash and you don't want to run out, like that would be embarrassing, right? So you're just like, I'm going to round everything up and then I'm safe. Okay. Some people might say round this to 30 to make it pretty. This 75 because they know 70 and 30 make 100, and so they might feel like that's more accurate. But my math lab might want you to use rounding rules, but estimation in real life is what you do in a grocery store or what you do to kind of, just get an idea of what it's going to be without using a calculator. All right, here. So we're going to assume a 40-hour work week. So if we take 1250 times 40, we can figure out how much they make in a week. And then if we take that times 52, we can figure out the rest. So let me clear. 1250 times a 40-hour work week is going to be $500 in a week. And then if they work 52 weeks in a year, that'd be what, 26,000? Okay. So if they do that, hopefully, did I type that in right? I think I did. So 500 and then $500 times 52 weeks. And I got, what was that? 26,000, something like that. All right. Next one. Okay. So this one of the people has to sit at the end. And so David, you know, he is picky. He wants to sit at the end. His other friends can, you know, sit kind of wherever. And there's 3 more of them. So he wants to maybe be on the aisle or here. He just doesn't want to be in the middle. All right. So what kind of an organized list will kind of help you here? So like, say this is David, so we'll call these people ABC. So ABC can sit this way, but is there okay if A sits here, say that's Anne, these 2 people can flip-flop, right? So then what if, I don't know, say B stands for Bob, I don't know, Bob has to sit next to David. Well, there's 2 ways Bob could do that, and then Anne and, I don't know, Carlos or whatever, Carlos, Anne could sit that way. And then again, who hasn't sat next to him? Say Carlos. So David has to be on the end, Carlos and Bob. And what? Carlos, Bob, and so I tried to be like strategic so I didn't forget anybody. Now that's 6 ways. If David's on that end, are you okay? It's going to be 6 on the other side too. So it could be A, B, C with David on this end, A, C, B, David, B, A, C, and B, C, A, again with David on the end. And what's left? C, A, B, C, B, A. With David on the end. So there's going to be 6 ways, both, you know, so 12 ways total. If you remember the multiplication principle, you can multiply choices. I have 1 choice for, say, this end. This slot right here, I had 3 choices. This slot, only 2 people are left. And then the last slot, there's only 1 choice. So there's 6 choices. When I do it this way, there's going to be 6 choices added up, get 12. So you could kind of do multiplication there too. All right, let's look at the back. All right, which is a better deal? So figuring out the price per ounce is a good idea. And again, money is always more important than peanut butter. So always type in your calculator money first. Sometimes you do have to go out a few decimal places. So that's 0.231, I would say. And that's money per ounce. And then the next one is $2.99. Money's first divided by ounces is, what is that, 0.249? So sometimes if you round, they might round to the same. So you need maybe an extra decimal place. But, so this guy is cheaper per ounce. So we're going to go with Skippy. Cheaper per ounce. All right, here in this one, if you have 50 cents off, so if I subtract 50 cents from that guy, now we only have what, $2.49 and 12 ounces. So let's figure out what that unit price is. So $2.49 divided by what, 12 ounces, 0.208, I guess, per ounce. So now suddenly this guy's a cheaper one. Okay, so if you have the coupon, suddenly Jif becomes the cheaper one. All right, this one, we just tried a bunch of different numbers. So say you pick a number 3, you add 4, you get 7. You take that new value, double it. So if I double that, I get what, 14. Then do what? Subtract 8, I get 6. Okay, so when I started with 3, I ended up with 6. And if we did a bunch of examples, if you started with 5, ended up with 10 and so forth. So we figured out that our original number always double. So if we pick n, we can see this. If you pick n, and what do? Add 4. And we want that answer first before we double it. And then after we double it, we're going to subtract 8. So if I do the algebra, distributive property, 2n plus 8 minus 8, these guys cancel, and you can see I have 2n. All right, so what is this called when you do a bunch of examples and you look at everyone's and you're like, it seems to double? That is called inductive reasoning. So inductive is when the information goes into your brain and you figure out a rule or formula. You're like, it seems like if I have 3, I get 6, 5, I get 10, 8, I get 16, 20 doubles to 40. So I know that whatever my starting number, even if I don't do this math, I know the answer is going to be doubling, right? And so that's called inductive reasoning. When you come up with some type of rule or formula after seeing a bunch of examples. Deductive reasoning. Deductive is more like law, like what a lawyer would do, or a judge, or a police officer. It's when there's already a law, like you have to drive 55 miles per hour. If I speed, right, if I go 67, they're going to pull me over, and they're not going to say, well, I kind of think you're driving fast. They're going to say, hey, we radared you. There's this law that says you have to drive 55. And guess what, Julie? You were not driving 55. So they're applying a law that already exists to me. And I'm like, instead of looking at a bunch of examples and trying to figure out the law, they have a law and they apply it to me. That's a deductive reasoning. So an example would be like in math using Pythagorean theorem. Okay. This theorem exists. I might have a triangle and I'm like, I wonder what the hypotenuse is. And say, this is 3 feet, 4 feet. You might be like, I'm going to use this guy's formula here. 9 and 16 is 25. The square root of 25. And you're like, 5 feet. This is deductive because you used a law or rule and applied it to a specific case. All right. Counterexample is when you come up with an example to prove something false. Okay. And so all prime numbers are odd. Prime numbers are like 17, like 1 and 17, or 3, 1 and 3. 12 is composite because it's 1 and 12, 2 and 6, 3 and 4. So the all prime numbers are odd seems to kind of be true. But then you're like, what about 2? Because 2 only has the factors 1 and 2. It's prime, but it's an even number. In fact, it's the only even number. So but again, it's enough. It's a counterexample. All right, let's look at this last one. Below is a pattern. Now we looked at this a lot of different ways in class. Some people saw like a square here, like a 2 by 2, 3 by 3, 4 by 4 with an add-on. Some people saw like, the bottom row is 1 more, so then 3, then add another one, 4, and then, you're always missing 1, Here, they're kind of like 1 more is 4, and then 2 more. And then at the top, you're missing 2 in the corner because when it's 3, you're missing 2. And when it's 4, you have 5 in the bottom. And then when it's 4, you have 4 tall. When it's 3, it's 3 tall. 2, it's 2 tall. And then the tack-ons and stuff like that. So you can view it that way. The way I saw it is I saw kind of a rectangle with the corners missing. Okay. So then on a 10 by 10, I would expect, let's see, on a 4, there's what? It's 5 and what is it? 1, 2, 3, 4, 5 by 5. Is that right? Or 5 by 6. Yeah, 5 by 6 if I fill that in. So this is 5 by 6. So this is what? 4 by 5. This is 5 by 6. This guy is what? 3 by 4. So on 10 then, I would expect it to be 1 more. So I'd expect 11 by what? 12? Okay, with just the corners missing. So I would draw this big square, pretend it's 11 by 12. So 11 by 12. And I would ditch all of this. So I would erase all of that. And I would just have 3 guys up here because they all have 3. And then here there's 1 in the corner missing, 1 in the corner, 1. So I would get rid of 1 in this corner. And then is that it? Yeah, pretty much. Okay, so I might use graph paper or something to make it pretty. The 0, 1 is a debate. The 1, 1. I think we could agree that when it's 4, it's 5, 3, it's 4, 2, it's 3. So I think we could agree it's 2. It's what goes on top of that might be the disagreement. They all seem to be missing 1 though. So I think you could make an argument, and there's always 3 in the top row. So you maybe could make that argument, right? And then here when there's 2, there's 3. So when there's 1, there should probably only be 2. So this is probably what I would go with, but only 1 over. Sorry. this, well, let's see, what do you do?